Hey everybody, we're talking about power functions and polynomials here. So we're going to start quickly with power functions. These are just power functions, are functions of this form. The conditions would be, I suppose, A could be any real number. Um we might want to prohibit zero. That could be kind of a trivial power function, but we can just say any real number. And n can also be any real number. However, we're really only going to be considering the case uh, where n is a non-negative integer. Okay, so n can be 0, 1, 2, etc. Um, you can consider, right, a power function can have any real number, so you can get negative numbers and fractions and irrational numbers up there, but we're really just using power functions as a stepping stone to the polynomials, and when we get to polynomials, we're only going to want positive integers or zeros as our exponents. So that's mostly what we're going to think about when we're talking about our power functions. Let's just take a look quickly at the power functions. And we're just we can really think about them in terms of even and odd powers, because those are going to give us the two biggest. Those are going to give us the big. Those classes will give us the biggest distinctions. Because all the even powers are going to share some particular characteristics, and all the odd powers are going to share some particular characteristics. So here I have our simplest power function x squared. And while we can scale these, I'm not going to worry too much about the scaling. So that's that a term in the beginning, right? If I multiply this by 5, it gets taller. If I multiply it by 1/5, it gets wider. If I multiply it by a negative, it flips it over. So that scaling, all the stuff from transformation still applies. But I think if we just look at the basic power functions, x squared, x to the fourth, and so on, we'll get the idea. And all the other stuff is just transformation. So the big idea with our even powers is that uh, they're symmetric over the y-axis, right? If we reflect across the y-axis, the graph would be unchanged, right? This is because if you square negative x, you still get x squared, right? And so swapping the x values from positive to negative doesn't change anything. As we increase the power, let's think about what's going to happen for large numbers. And all I mean by large in this case is bigger than 1 or smaller than -1. So outside of the interval 1, 1, -1, 1. Squaring them will make them bigger. And taking them to the fourth power will make them even larger than squaring them will. And so we expect the graph to get larger quicker outside of -1 to 1. Between -1 and 1, we expect the graph to get flatter or closer to 0, because if you take something smaller than 1, like 1/2, and square it, you get 1/4. But if you take it to the fourth power, 1/2 becomes 1/16. 1/16 is a lot smaller than 1/4. It's a fourth of the distance to the x-axis, and so all those points below 1 will be pulled down towards the x-axis. And at -1 and 1, nothing will change. -1 squared, 1 squared, -1 to the fourth power, and 1 to the fourth power are all 1. So let's just look at that picture. So we see here, I'll zoom in a little bit, exactly what we said. We're still going through these 2 points. Inside those points, the purple graph is going up more quickly. Right? The purple graph is going up more quickly. But between those points, it's flatter, right? We can see it kind of pressing down to the x-axis. If we go up to the 6th power, that's even more exaggerated. Flatter in between, steeper outside of them. And we can play with increasing the power. So here the red graph is x squared. And as I increase the power, in this case, I'm going up to the 40th power, x to the 40th, we can see how very flat it is in here, right? It's not actually flat. This red graph is not sitting on the x-axis, although we can see right now Desmos is outputting 0, but that's just rounding, right? We're taking a number like 0.25, well, whatever, something close to a quarter. That's close to a quarter, and taking it to the 40th power is incredibly small, and Desmos is just rounding it to 0. It's not until we get out here, right, we start to see, 0.8 there to the 40th power is still incredibly small. It just passes the threshold to not be rounded to 0. So that's the idea with our even power functions, right? So even though there's obviously differences, these aren't the same shape, we're still symmetric over the y-axis. We're still growing without bound as we go. As our x values get larger and larger, we're growing without bound, meaning the output values are getting larger and larger, right? If you the larger you put in an x value, the larger the output, and the same for our negative x values, right? So our graph is going off towards positive infinity in both directions, in the positive x direction and the negative x direction. Okay. All right, let's compare this now to the odd power functions. And the simplest example is x, although x is a little bit of a special case. So we usually look at x cubed, because while x satisfies one of the properties we want to notice, which is that this graph is symmetric. We say symmetric about the origin, which you can think of it as saying if we rotated this graph by 180 degrees, it would look the same. But once you get to powers greater than 1, odd powers greater than 1, we get this characteristic curve in the middle, this little bend in our odd power function, right? So this is x cubed, and you can see how it flattens near 0 and then becomes steep again. And we'll see a very similar pattern that we saw with x squared, in that the higher the power, the flatter our graph gets between -1 and 1. The output values are all closer to 0 than they were for x cubed. And then outside of -1 to 1, the purple graph is getting larger more quickly, right? So at this value, let's say at x equals 1.1, the output is 1.89, whereas on the orange graph, right, we're significantly lower than that. And then let's do the same game. Let's scroll up through some powers. So we're starting at x here, and now there's our cubic, and then we start to, let's make it a color other than black so it doesn't disappear into that. Let's try blue. Right, as I scroll up, we're getting flatter and flatter and flatter, right? And again, it looks like it's just sitting there on the x-axis, but remember, each of these outputs, even though Desmos is telling me 0, the number that's actually our output, the y-coordinate there, is -0.404 to the 39th power, right? Which is not 0. Let's just, what did I say, 0.404 to the 39th power. Right, now this is an incredibly small number. If you can't read that, it's -4.5-ish to the times 10 to the -16th. So there's going to be 15 zeros and then a 4, right? 0.15 zeros and then a 4 and the rest of that number. That's incredibly small, right? And so it's just being rounded to 0, but in actuality, it's not 0, right? So only at the origin is the output actually 0. It's just so small everywhere else that Desmos is just rounding it, right? And then it almost looks like this graph is perfectly vertical, when in fact, it's just incredibly steep. But anytime you for this vertical part, it's always the case that if you increase your x value, you're increasing your y value. It might be a little hard to see, but right, if I increase by just a little bit, right? So look at my x coordinate, goes from 1.0073 to 1.0076. The y coordinate, though not changing a huge amount, is several orders of magnitude larger in change, right? Because it's changing at our second decimal place instead of only at our fourth decimal place. So in any event, that's the characteristic features of our even and odd powers, right? We can see the same thing here that we saw, or a similar thing with these higher powers, that if we rotate by 180, we have it's symmetric, right? The graph would look the same. And also the same thing, right? We can always scale these, right? So if I put a 1/2 in front of this or a 1/6 in front of it, we're compressing it vertically, or I could stretch it vertically, right? But the general shape is going to stay the same. So that's why I just looked at the ones with the 1 as the coefficient. Okay, so that's the basics of our power functions. We're going to come back to this idea because it turns out to be useful for some stuff with polynomials. But let's jump into polynomials and talk about what they are. So polynomials will have the following form. All right, so I'll call them a function, f of x, and I'll explain what all this is after I write a few terms. A sub n times x to the n, a sub n minus 1 times x to the n minus 1. Right? We just continue in that pattern. And then I'll say more about that in a second. Plus a sub 1, x to the 1, plus a naught. Okay, so here, let's put some conditions on what these are. These a sub i's, all these a's with subscripts, are just real numbers. The only condition is that the first one is not 0, right? Because well, let's come back to that in just a second. And we're going to have n is just going to be the non-negative. It can be any non-negative integer. Okay, you can choose any non-negative integer to be n. So what this is saying, let's just do a couple of examples, is we might have something like this: 3x to the 7th plus 4x to the 6th minus 12.3x to the 5th plus 0.007x to the 4th minus 2x cubed plus x squared minus 2x plus 1. Right? There's an example of a polynomial. These constants are what we call the a sub n. There's secretly a 1 here that we're not seeing. Those are our a sub n's, our a sub n minus 1s. In other words, we've chosen in this particular polynomial to have n start at 7, right? And so this would be a7, this would be a6, this would be a5, a4, a3, a2, a1, and a naught, right? That we just have, which is a way to label what those coefficients are, okay? The one that's attached to the x to the 7th, we call our a7. The one that's attached to x to the 6th, we call a6, and so on and so forth. Let's write out a couple of other examples. Let's say y equals 5x cubed minus x plus 7, right? So notice something here. It seems like we're skipping over the x squared term, but what we can think is it's just 0x squared, right? We don't write that because it's just a waste of writing, but it still satisfies this definition we gave, that we start at x, whatever we start at. So in this case, we're taking n equals 3. We go on down the line. We have an x cubed term, an x squared term, an x term, and a constant term. But any of those besides the first one can have a 0 coefficient, so they may not all appear because we won't write them, right? So even if we have something like y to the negative 5x to the 1000 minus 2, right? That's a polynomial. It's just that every other coefficient, 900, the 999, A998, A997, A996, A995, and on and on and on, are all 0 except for A naught. So it's only got 2 terms, right? And that's perfectly reasonable because the only one that can't be 0 is the top term, right? So the reason we don't want that top term to be 0 is because we call this first term, this is a very special term for our polynomial. So we call, well, let's just look at this first term. Okay, so a couple of things. The n, well, this whole thing we'll call the leading term. A sub n we'll call the leading coefficient, and n is the degree of the polynomial. Okay, so the power on x we will always call the degree, right? So if I wanted to refer to looking back at this polynomial, I might say, let's look at the fourth degree term, and that will be this term right here is our fourth degree term. But when we talk about a polynomial, we'll talk about the degree of the whole polynomial and what we mean. So let's make this clear. This is the degree of the polynomial. The degree of the polynomial is the degree of the leading term. So this first polynomial I wrote that begins with 3x to the 7th is a degree 7 polynomial. And this one that began with 5x cubed, that's a degree 3 polynomial. And the last one I wrote is a degree 1000 polynomial. So that leading term is how we one of the ways in which we classify our polynomials, right? And just to make it clear, since I arbitrarily chose numbers that all have odd degree, we can certainly have something like this, right? There's a degree 6 polynomial. So it doesn't, whatever the leading term is, again, that's a degree of our polynomial. One of the reasons that we look to the leading term is because whatever that leading term is, that tells us a lot about the behavior of our function. So let's look at some more general polynomials. So here I've got a degree 4 polynomial, and I've got several of them, right? So I'll just kind of scroll through these. They've got these right now. Remember our power functions. Here's our power function x to the 4th, goes through 0. It's symmetric over the y-axis. As we start adding these other terms, things get a little more complicated, right? We see these characteristic kind of looks like a hill or a valley, right? We've got these little extra bumps going on in our polynomial. This is pretty typical behavior. However, that behavior, all these bumps, happens, we would say, near 0, right? Near 0 is a fairly arbitrary term in the sense that I don't mean any particular value. Near 0 might be, it's just some interval containing 0, right? So in this case, I might say between -4 and 4 is near 0. And all these twists and turns in our graph are happening in that interval. If I had a different set of coefficients, near might be between -10,000 and +10,000, a much bigger interval, right? What's important about that is that at some point, the twists and turns stop. And if we look at our graph far enough away, here's those same functions. There's a couple of them. The orange graph we see, it's the one in the middle, is our x to the 4th power. The other two are these other 4th degree polynomials that I have here. And we see that as we zoom out, all those twists and turns, right? That's all happening in this tiny little flat area between like -4 and 4, like I said before. It's all down there. But at this, look at the scale of our y-axis. We're zoomed out pretty far. None of that stuff matters from this perspective, right? It's all lost in there. We can't see the difference. And our polynomial just looks like x to the 4th in the sense that it's just getting larger and larger as we go towards positive and negative infinity. And this is going to be the case all the time, that whatever our leading coefficient or our leading term is, when we think about what happens to our function far away from 0, far away just meaning eventually, right? Other ones I might have to zoom out even farther. In fact, we'll see one in just a second where I have to zoom out even further to see this. But eventually, it will just look like the power function that is the leading term, right? So in the case here, I just have x to the 4th. But if I had 7x to the 4th plus whatever else terms, it will start to look like 7x to the 4th. Or if I had a negative, it would be flipped over and look like that. Let's do the same thing with our degree 5, looking at an odd power function. So there's x to the 5th. If I throw some other coefficients on there, here's -x to the 5th plus 2x to the 4th plus x cubed minus 2x squared plus 0.5. Notice all the twists and turns there. Here's another one. Here's another one. All right, a whole bunch of stuff going on. And near 0, right? These look very different than that blue graph. They've got a lot of different stuff happening, all these twists and turns that the blue graph doesn't have. But if I zoom out far enough, right, so just to be clear, this is, so here's the picture zoomed in. These are the same two functions zoomed out. Again, look at how far out the scale on that y-axis is. But at that, from this vantage point, these graphs are looking very, very similar, right? Because that x to the fifth minus 10x to the fourth plus 20x squared minus x, far from 0, begins to look like x to the fifth. Right? We can kind of understand why that might be. Like, let's compare x to the fifth to this 10x to the fourth term, right? So for example, if I let's put in a large number, like let's put in 30 to the fifth. So there's our leading term, x to the fifth, when we evaluate it at 30. And then let's take 10 times 30 to the fourth, right? So, right, these are both large numbers the way we think about them, but this the 200, this 240, what is this? Let me count zeros. Sorry, 24 million is a lot bigger than 8 million. It's about 3 times bigger, right? So that's a significant amount bigger. If we make 30 even larger, let's take this up to 100, right? And we're about 10 times bigger, if I'm counting correctly, right? So that's significantly bigger, right? We started out about 3 times bigger, and by the time we got to 100, we're 10 times bigger. In other words, the difference between x to the fifth and x to the fifth minus all that other stuff, the larger that x is, the less that other stuff matters, because that x to the fifth is so big. It doesn't not matter. Those are still large numbers, but you know, a billion to the fifth is a billion times bigger than a billion to the fourth, right? And so when you're comparing those two things, even though a billion to the fourth is like incomprehensibly large, it's a billion times smaller than a billion to the fifth. And so it pales in comparison. And so that we say that one way we can say is that leading term dominates, okay? And so we end up in the same place, in that to the positive x values, our function is going off to positive infinity, meaning the larger the x value we put in, it just keeps getting larger. And in the negative direction, the same thing happens, just negative outputs, right? And so regardless of all that other stuff, all those twists and turns we saw originally, eventually, right? Because near 0, that 10x to the fourth can matter a lot, right? If you just put in a number like 2 to the fifth is 32. 10 times 2 to the fourth is 160. So near 0, that number matters a whole bunch more, right? That 10, right? This 2 to the fifth is really 2 times 2 to the fourth. So the one with the 10 in front is actually bigger than that there, right? So near 0 it matters, but eventually that fifth degree term is gonna be bigger and dominate all the other terms. Okay, so let's see, what else do we want to see? So we want to just kind of understand a few characteristics of our graphs. Let's look at this one. This one seems a little better. So a couple things to note. So there are these turning points on our graph, places where our graph goes from increasing to decreasing or decreasing to increasing, right? As we approach this point, for instance, we're increasing, and then we decrease on the other side. Then we decrease till we hit this point, and then increase after it, decrease, increase, right? So we have these twists and turns. The other important feature when we're looking at behavior near 0 are these roots, right? Roots are another way of saying x-intercepts, places where our function is equal to 0. Sorry, there was too much on the screen there, right? So we've got, in this case, 5 places where our function is equal to 0. Okay, again, we call those roots. And then we also have a y-intercept. In this case, because this one goes through the origin, the y and x share an intercept, but that's not always going to be the case. Let's just glance at, for instance, this one has a y-intercept that's a little higher. Also notice this one only has 3 roots, but it still has 4 turning points. Let's see. Then this one we looked at. This one has, let's see, 4 roots. Oh no, there's 2 roots hiding in here, and then it has 4 turning around points. So let's look at our 4th degree polynomials. Right? They have similar kinds of things. Here's one that has degree 4 polynomial that has 2 roots and it has 3 points where it turns around. Here's one. Here's one with just 2 roots, or the same 2 roots and 3 points where it turns around. So there's a lot of deep theory we'd have to go into to explain all of this. But the result is that our polynomials, we have a few rules that we want to make clear. The number of roots is always, let's put it say it another way, is never larger than the degree, right? For polynomials, right? So a degree, we saw this with quadratics, that that's a degree 2 polynomial. Quadratic is a special case of a polynomial. They could have 0 roots, 1 root, or 2 roots, but it can never have 3 roots. Okay, and this holds for all of our polynomials. A degree 7 could have up to 7 roots. It might not have 7 roots, but it could have up to 7 roots. Odd degree will have at least 1 root. Have at least 1 root, right? And the simplest way to see that is that, well, we know that as x gets larger, it's going to be spitting out larger and larger positive values, and when x is really, really negative, it's going to be spitting out larger and larger negative values. And because our functions are continuous, right? We haven't really talked about this yet. We're going to talk in more detail later about this, but just meaning that there's no breaks in it. To get from those negative numbers to those positive numbers, it has to pass through 0. And so it's going to have at least 1 root, but it might only have 1. Even degreed polynomials don't have to have any root, as we've seen before. Let's see. And then the turning points, the number of turning points is never larger than the degree minus 1. All right, so it's never going to be more than 1 less than a degree. So quadratics have 1 turning point. They're degree 2, 1 turning point. Cubics can have up to 2 turning points, right? We saw something like this. They can't have 3 turning points or more. Even powers will always have at least 1 because they're going to need to, if they might be this shape or this shape, but they're going to have somewhere, or they might have more than that, but at some point they have to go from their that classic U shape that we saw in the beginning. Whereas something like a cubic, it can flatten out, but then continues going in the same way. It doesn't actually have a turning point. So let's just say a couple other things about that continuity. So continuous is a topic that you get into more detail with in calculus, but the general idea, you may have heard this before, is you can draw it without lifting your pen off the paper, and that's a good enough intuition for now, right? It's a little hard because we're going off to infinity, so you couldn't actually draw it. But if you look at any part of it that you're looking at, you're going to always be able to draw it this way. It just keeps going. There's no jumps. Like, it never does this, right? It never has a gap or the function stops and restarts or something like that. It just keeps going continuously. We also say that our polynomials are smooth. Let's write this down. Continuous and smooth. And again, this has a technical definition, but for our purposes, it just means it has no sharp corners. Has no sharp corners. That you'll never see something like what you see with an absolute value function where it has a corner like that, right? When we turn around, it's always a rounded edge that's turning around, okay? And then we'll get more into this later, but we can always write our polynomials factored to some degree. So, for example, the polynomial x to the fourth minus 3x cubed minus 28 can be written as sorry, I misread my notes. Can be written as x squared, x minus 7, x plus 4. All right, so we'll look at some examples of factoring, but just we can do some factoring there to get this. Here's another one: 2x to the fourth plus 7x squared minus 15 can be written as 2x squared minus 3 x squared plus 5, right? And so there's always possible to write it in some, let's say theoretically possible. Finding the factorization is not always easy. These are some examples where our factors are easily found with these integers. Sometimes it's not really possible for us to find them, but we'll talk more about that in another video. That is it for this one. Thanks, everybody. See you next time.